gRPC tape. So yeah, we just wanted to do a talk on putting gRPC in practice. Basically, what we wanted to do was sort of like have a sort of light agenda and give a little bit of an overview of gRPC. Talk a little bit about some practical problems that you might encounter when you're actually managing a code base that uses gRPC, that uses proto files and sort of like generally files that sort of represent some sort of API surface. How do you deal with that? What are the sort of some of the evolving sort of patterns that we're seeing over there? Just wanted to give an update there. And then thirdly, like, some discussion about scaling gRPC, about how do you load balance services? How do you actually introduce a little bit of redundancy? What are your options available over there? So we want to talk about these few topics. We're not touching on topics like observability. We're not touching on like debugging and so on and so forth in this talk. But definitely, if you have questions on those topics, feel free to ask the group over here. And we'll do our best to answer those questions. Yeah, all right. So, oh, an overview. Okay, so show of hands, how many of you have actually used gRPC before? Okay, so a few, so it looks to me like a lot of you have not. So I think I'm gonna go a little bit slower on these first few slides. So basically, gRPC stands for gRPC Remote Procedure Calls. It's a recursive acronym. Vijay named it that way. So it's a high performance, standards based, open source, blah blah blah. It's an RPC framework, okay? And it's actually evolved from stubby RPCs, which are actually used in Google. So over the past few years, Google has been sort of open sourcing some of these technologies. Like if you see Kubernetes, it came out from Borg. If you see something like Stackdriver or some of the open census work that we're doing came out from the work that we've done around Dapper and so on and so forth. Some of the work that we're doing in gRPC, it came out of maybe about a decade's worth of experience doing stubby. So basically, like we have tens of billions of RPCs per second in Google. This is probably an outdated number at this point. But basically, like what caused us to actually build gRPC, right? Like we built it to address an actual need. In the past, if you look at Google, it was pretty much an online company with the primary mode of accessing Google services was through the web. But over time, it's changed. You access Google through mobile phones. You access a lot of our cloud APIs. You access it through like your phones, your speakers, your TVs, from balloons and so on and so forth. So we wanted to sort of say, what would a next generation RPC system look like if we were to take something like Stubby and sort of build it for this future vision of Google, like with self-driving cars or whatever, right? So that's kind of like what gRPC, what the main motivation of like building gRPC. RPCs in general are an old concept, right? Like you might have had a good experience with them. You might have had a bad experience with them. I don't blame you. It's an old concept, like, things like Corba and so on are all like RPC systems. But basically, like basing this on Stubby, we believe that we've had good success. So this should be a good paradigm that, we can sort of like open source and sort of build a custom protocol that allows us to expose a lot of our high performance cloud APIs on. In Google, like in terms of usage, we use it for a lot of our cloud client libraries. We also use it for mobile apps like Gboard, like the Google Keyboard, Allo, Duo, these kind of apps a little bit. And internally within Google for microservices, like since we already have Stubby, we're in various stages of adoption of gRPC internally. So that's much more sort of like teams find value, teams over time sort of like adopt it and so on. But it's definitely intended for that purpose as well. Just like what's a gRPC? What's this thing that I keep talking about? So it's basically an RPC system, and the idea here is that we present a particular service contract to sort of say, here's we provide a consistent way of defining a service contract. And what the gRPC framework allows you to do is it allows you to generate everything in green in this particular sort of diagram. Everything in green is generated from that API contract that you specify. Everything in yellow is actually the application logic. Basically, it allows you to write server-side stubs that implement an API contract. It allows you to write client-side stubs that actually call into that server-side API contract. And it lets you, as an application developer, focus on the business logic that you need to actually focus on. And the nice part about this is that it works really well in a polyglot environment. It gives you a layer of consistency when your teams are doing Python, when your teams are doing, some teams are doing Python, some teams are doing Java, some teams are doing Go. But ultimately, all these teams talk to each other in the same consistent sort of format. So that's been pretty useful over time. So yeah, so and another part about moving to microservices, right? This sort of pattern of building services lends itself to this whole microservices thing. Can I get a show of hands on how many people actually would boldly say that, hey, I work with microservices in my... All right, okay. Not everyone raised their hands. So basically, in such situations, right, it's normal. But if you actually specify a big, large API contract for a particular app, over time, certain hotspots, you would be able to sort of piece away and break it up into a separate service by taking that piece of the API contract over, splitting it out, refactoring your application into a smaller stub somewhere else. So gRPC kind of like helps you with that iterative pattern to sort of break down a larger service into smaller pieces. And it's often a cyclical process, right? Like you would start with something that looks like a microservice. Over time, it'll grow to 2 heads and 3 legs. Then you'd want to like separate that into a smaller service again. So it's an iterative process, and being able to sort of speak in terms of contracts kind of like facilitates that. So, okay, so you decide, all right, this sounds fantastic. Let's get into this microservices architecture, right? How do you then design this stuff? So that's the next question. Like, okay, so we have this gRPC thing. I think I'm going to do it. How do I define these APIs? Should I just go and write a bunch of APIs, write a bunch of methods? So some tips over here, right? Like some old systems like Corba led to a proliferation of methods, right? Like you would say for everything that you want a particular service to do, you define a method for it. But remember, APIs are forever, right? Like it's really, you should design your APIs as if they're forever. And what that basically means is that stick to best practices that have grown over time, like with HTTP and REST and so on. Like stick to a resource-oriented design. Start by defining the data structures that a particular sort of application would sort of talk about, the resources. Like for example, if you want to talk about, say, a contact list, it has multiple contacts, and each contact has a name, a phone, and so on. So you define that data set. Then after that, you start to think about the small sort of methods that you can use to sort of manipulate each of these resources. So you then define the service methods on top of this. So, and then once you sort of define these methods, you sort of have an idea of what the business logic of these methods should be. And again, like when I say resource collections, like I mentioned like an address book example before, but it doesn't always imply a database, right? It could be a pub sub queue. It could be some real-time analytics data that you get some information out of. So even like a random number generator, right? Even in such situations, it helps you to focus a little bit on the resource and then design what that resource is and how that resource should be accessed. So that's some sort of a best practice, I would say, to keep in mind. Some other common patterns that we see is the usual operations that we see defined on resources are create, update, get, delete, list, you know, these kind of operations. And if these don't fit your sort of, don't fit the sort of your application that you're looking for, then in such situations, right, don't try to force your design into that, because you can always reach out and define a custom method that's like maybe a watch method that sort of watches a particular resource for changes and then publishes a message back when that particular resource changes. You have that flexibility with gRPC as well, but it's often useful to start from this core set and really reach out when you need to. So that's some of the general principles of what an RPC system is, and some of the design guidelines. Let's look a little bit into protocol buffers and sort of how they help you define or put into practice some of these points. Are all of you familiar with protocol buffers? I assume not, actually. A couple of people. Okay. So protocol buffers is basically, for gRPC, it's used as an interface definition language. It's used as an IDL to describe a particular service. It's also used as the data model, which means that in addition to sort of defining how a service is, it's also used to define what information that's sort of the resources, like what kind of information is passed back and forth, what the resources are. It's also the serialization format that's used along the wire. So protocol buffers can actually serialize your messages into a very efficient binary format and send it across the wire. The nice part about protocol buffers is it's strongly typed, so you can actually have a very good definition of your APIs, very crisp. That's well typed. You don't lead to ambiguity. Is this a number or a string, right? Like you don't lead to that kind of ambiguities there. That's basically the lingua franca of Google at this point. So in this slide, I guess it's self-explanatory, right? There's a person. The person has. We first define the messages first. We first define that there's a person type, there's a phone type within that person, and then there's a phone number type as well. And the phone number can be one of the phone types. And then at the very end, we have the phone number, which is a repeated field. A repeated field means that it can have one or many of that particular records, basically. This is standard Proto 3 specification. I won't go too much into it. If there's like documentation available on the web you can look through. I just want to give you an example here. So so one of the things that you do is, okay, you define some of these messages. I've given a little bit more examples over here, and the top section is a service definition. This is the gRPC section of it. That's the part where you actually define the RPCs. So there's an example. The top example over here is a unary RPC. You send it a point and it returns a feature. The second part is you see the keyword stream that's used to prefix some of these arguments. That is actually states that it's a streaming. The request is a streaming request. The response is a streaming response. So that's an example of a bidirectional streaming RPC. What that means is that the request, there would be a stream of requests coming in and a stream of responses coming out. So it's a bidirectional stream, basically. So yeah, so those are the sort of services that you can define with gRPC. And what you would do then with the service definition is you would use a Protoc tool with the gRPC plugin to actually generate the client-side stubs and the server-side skeletons to actually define your business logic over. And you should just be able to write the business logic for these methods according to your language of choice. That's pretty much, in a nutshell, what gRPC does for you. Any questions so far? Yes. Yes. So it's basically you implement the stubs and then you implement the server-side skeletons. But I mean, the management comes in many ways where gRPC takes care of certain things for you. Once you establish a channel to a server, for example, the underlying connection, if it gets disconnected, for example, gRPC will automatically reconnect. There's also other things like ways in which we have in gRPC where you can actually do, you can resolve a particular DNS name into we support mechanisms for service discovery. We support things like health checking, keep alives. So a lot of the stuff that you would normally do in terms of management is pushed into the gRPC layer. So there are other things like stats, tracing, and so on. Information can be extracted out of a service for your observability needs. Yeah. Yes, yes. So that all this code is actually like part of gRPC as well. And there are like health checking as a service, for example. There's a standard service that you can use for health checking that you could just sort of pull in the reference implementation of the server side, and the client side just sort of call into it. The other thing gRPC also enables is on the application level, we have what you call interceptors. Most of the languages have this way of hooking into this interceptor, so you can lay on concerns like authentication, authorization, and so on before every RPC call goes in, goes out. So there are hooks available at the top level. But the idea is that with this sort of, I just wanted to get the essence of gRPC out, because that kind of like helps you build a lot of these concerns on top of. So, okay, so you bought into this, you drank the Kool-Aid, like, all right, I'm gonna go, I'm gonna go microservice everything. And then you will have two problems. You'll have many protos, right? One, you'd have to implement all this logic, and two, you'd have to manage all these proto files. The proto files will change faster than you can actually write them, and soon you will not know which version of a particular protocol, which service is speaking. So some best practices that we have sort of talk about, we wanted to share, like, you sort of decided to go with gRPC in production, some things to keep in mind. Question for the audience at this point. How many of you actually work in an environment where everything, all your source is within a single monorepo? That's 3 people, 4, 5 people. The rest of you don't. So basically, you will have a situation where you have one team building service A, and you have another team building service B. Now, the team service A they're going to have to manage their proto in some way. Service B is going to have to manage their protos in some way. And then suddenly you're going to feel like, hey, I want to pass along a context that's specific to my application or my ecosystem. Where do I put this common proto, and so on? So there are these concerns that will pop up. And here are some sort of general principles, right? So a proto file is a contract. So be very careful in sort of making changes to your proto file. APIs are forever, right? Try to establish as a policy the single source of truth for each proto file. You want to make sure that all your proto files, you are easily able to say, that's where it should be. That's the single sort of source of truth. All these other copies, if any, are not, they're not sort of canonical. Don't copy. If you copy, have tooling to make sure that you can identify when copies go out of sync, when copies can come back in sync, and so on. But really, don't copy. For operational simplicity, right? Like, share proto files. Share read-only versions of your proto files, but do not share generated SDK code and so on. That leads to you doubling up as an API SDK maintainer. That means that you suddenly be in the business of shipping SDK libraries in multiple different languages, supporting multiple different versions, even though all you wanted to do was to write a proto file and write your business logic. So don't get into that business. We're in that business, and yes, don't get into it. Okay. So one way of achieving some of those principles is to use Git submodules. If you use Git, you can always submodule a particular repo containing the proto files. And you can fix a submodule at a specific commit, and the owner, that puts you as a client in control of when you want to update that submodule and so on. Now, protos can actually be backward compatible. They are designed to be backward compatible. They allow you to sort of ignore unknown fields. They allow you to sort of like evolve a particular API over time. So if you design a service API carefully, it can last you a few years. And after that, it'll grow some sort of like things, and you'll be like, okay, fine, we need to do a new service. That'll happen, but this is okay because protos are generally backward compatible, so having a slightly out of date submodule is fine. So teams don't have to coordinate their release processes over time. They can just sort of ship whenever they want. So some options, right? One is create a shared repo within your organization that hosts all the protofiles, right? It's shared by multiple sort of projects. It's a good approach for sharing common concerns like what do we log, how do we log, what's a structured logging API going to look like from every application. The positives is that it's a single source of truth. The negative part is that you need a centralized entity to then own this. Which infrastructure team is going to own this? That becomes a big problem. And then who's going to commit changes to it? So then it becomes a big problem whereby so if you put all your protos in the same sort of a repo, you would have this onerous red tape process of updating protos in that when those protos don't really belong to that team, like it belongs to your team. So that's a problem there. So then you go the other way, right? Like each team has its own protofile. It basically maintains two repos. One is just their protos with their sort of API contracts and definitions. The problem with this, of course, is that if you're a client, you're going to be importing like 50 million protos depending on what your client app does. If it's like a mobile app for your entire backend, for example, you could end up importing a lot of protos. So that's the downside of sort of doing this. What we would really recommend is like a hybrid of these two. Figure out what the common concerns are. Put that in a single shared repo for that's shared organizationally. Keep it minimal. Give it a proper owner, like maybe the infrastructure team or somebody who really cares when some of these things break. And then for each service that may not sort of like that may not like belong, that may not sort of yeah, just put it in your own separate repos. Basically, like not everybody cares about it. So and then clients and services can actually import these as Git submodules. It keeps your concerns small, and you import what you use basically. So that's pretty useful. Of course, if you have a mono repo, this solves a bunch of the problems as well, whereby there's a single source of truth for all your source code. But that's usually not an option these days. And here are some general sort of guidelines of trying to make sure your protocol buffers are generally backward compatible and then you don't break things. Basically, each sort of resource in your protocol buffer has a tag number. Don't reuse it. Like, don't change one particular tag. Don't when you're refactoring a proto, try to use a different tag. If a particular resource is sort of deprecated and you want to use another resource, just use another tag number. There's like you can use like maybe 4 million tags, so you have many. Don't make a message with a lot of fields. Like if you have like hundreds of fields, try to refactor it into separate protos and include them. And then don't go from a repeated field, like say we saw the repeated phone number field, into a scalar field. That usually breaks backward compatibility. And of course, do define message types in separate files. Reserve tag numbers for deleted fields. If you delete a particular field, don't reuse that tag number, basically. And one other rule that's generally applicable is keep your proto compilation as a separate step in whatever that you're building, so that when it breaks, or if that particular rule breaks, you kind of know. Yeah, so that's my part. I probably ran a little bit over time, but Vijay is going to talk a little bit about scaling and so on. That's a good question. I will no, but that's a good question, because this keeps coming up, and we're actually starting to explore like what would something like that look like.
And the way that I would view it, but Yeah, that's right. They have that. But what I personally view it as is that a proto change is an API change. And so at least to avoid API breakage, basically, we always, on all of our pull requests, we have a detailed set of end-to-end tests, right? So I think something like 23,000 tests run on every gRPC pull request. And so if something is, of course, a pull request that has proto changes and end-to-end test changes in the same API should trigger 100 suspicions, and so the reviewer should really be paying attention to that. But if it's just proto changes that are breaking without changing every one of these end-to-end tests, some of the end-to-end tests will fail. So that's what we're sort of counting on, is that sort of test-driven development is the Google model, which you've probably heard of, from being the Google model, that is. And so we would just view it as an API change like that would, if it breaks backward compatibility, would end up breaking one of the end-to-end tests we have, if we have sufficient coverage. And if we don't, then that means you don't have sufficient coverage, and go increase the coverage. Yeah. But
one of the things that we're seeing is that this particular proto management, right, is a common problem that teams face when they start to deploy gRPC in production and so on. So we're actually trying to figure out what would a solution for something like this look like, and trying to engage a few folks in the community to sort of get feedback and try to figure out should we do a proto registry, for example, that sort of takes these concerns away from, separates these concerns from source control management. What would such a solution look like? So if you're interested, just let me know offline, and as I start to sort of spin up some of these conversations, I'll make sure I involve you and sort of see what a solution looks like.
Yeah, this actually, oh, all right. This is actually perfect, by the way. You should definitely talk to Kailash, because he just recently transitioned to becoming a product manager, and this sounds like the sort of great product that he would love to manage, I'm sure. So this would definitely be his thing, right up his alley. So I want to actually shift gears a little and talk about gRPC and load balancing. I guess, so now we've all bought into the gRPC story. How many of y'all have worked with solutions like Kubernetes, for example? Is it anyone? Okay, great. So once you've got your production ready service ready, you're going to want to deploy it on something like Kubernetes, perhaps, and actually get it packaged up in containers so that you have a nice sane system that you can run. And then you have, with your Kubernetes cluster, you can have it make it sort of, be able to automatically assign where things are going to run and so forth. But then we get to the next question, is what happens once you need to scale it? And so in order to come to that part of the story, we're going to talk about load balancing and how gRPC plays into load balancing. Again, show of hands sort of thing, is how many of you have experience with load balancers? Just out of curiosity, maybe we'll do it on an item-by-item basis. Anyone using Istio or Envoy? Okay, let's do some other ones. Linkerd, yeah, Linkerd, Nginx, Nginx, yeah. Okay, sorry, I don't know if that's pronounced properly. Okay, so there's many options. But basically, the reason that we're going to want to scale something in a microservice architecture is to build scalable services, is to be able to push your throughput beyond a certain level, to be able to decrease your latency by reducing the load on specific nodes. We don't want to overload a single backend, right? So we want to go through very carefully and avoid that problem. At the same time, we want to make sure that if a backend fails, some other backend will be there to pick up its. So we're going to have fault tolerance that way as well. And then finally, another feature that is very critical is the fact that when services get updated, we want to do it in a hitless fashion, or relatively low hit fashion in any case, but ideally we can do it hitlessly by doing things like, first transitioning, say, 1 or 10% of the backends. And if those work, then we have reason to believe that the service actually does work now. And then we can transition the others in batches like that, so that the new version of the service slowly starts picking up the load, and then we're convinced it works. It gets all the load, and eventually the last of the old services is taken off. The last of the old version is taken off. And so it allows us to do that in a sort of incremental way, and thus is a key part of actually making our microservice architecture work. So some concepts of load balancing. We have some different flavors of load balancing that we're going to talk about. One of the basic distinction is where we put the load balancing logic. In the case of what we call proxy load balancing, the client is sort of in the data path. This is going to be where the call is handled. So the client is going to be connecting to a server, right? As far as the client knows, it's a server, but the reality is not a server; it's a load balancer. So the client is actually the server is actually a load balancer, and the real servers, the ones that are actually running the microservices, are sitting behind that. So you can do this with any old client. The client that you are using on an unbalanced architecture will work fine with a proxy load balance architecture. That said, doing this often means that you have an additional step of latency because you're going from the client to the proxy to the real servers. In order to reduce that on Kubernetes, the very common model of deployment is what's called a sidecar. In a Kubernetes pod, you will have two containers very often, where one is the application and the other is the proxy. They live on the same host and they share the network, being that they're on the same host, but because they're in separate containers, they're relatively isolated from each other. Okay? So we can have a sidecar proxy for actually doing that load balancing. And so that way you're at least not having the full latency impact of a network transition against the proxy, network config. Okay? Or you can have client load balancing, where the actual load balancing logic is implemented by the client using, for example, information coming from DNS. You know, the gRPC by default includes DNS round robin. So when you get a DNS response, it gives multiple server backends for the name. The client load balancer can automatically just balance the load between those. Typically, that said, the nice thing about client load balancing is that very low latency. It doesn't have an additional hop of overhead, but it tends to be only good for having simple load balancing logic, which is often fine. You know, in many circumstances, especially if you control the client and you control the server, like if it's entirely in your intranet, if it's entirely behind your wall, then you can actually do that pretty easily. Okay? But if you want to start adding more complex functionality like load monitoring and so forth, you probably want to use something like the proxy. Okay? And that's where we get to the service mesh model that we really recommend and see as the model going forward that most of our load balancing users are using. In this situation, we have a service mesh like an Istio mesh running here, where we have Kubernetes set up. We have multiple Kubernetes pods. And each one of these on the client side will have the gRPC client application along with the sidecar proxy. And that sidecar proxy is the one that's actually talking to the servers, which themselves in this case are have a sidecar as well living with it. So the load balancing is performed entirely by the proxy, and so there's additionally features that the Kubernetes API can provide to do things like load monitoring and so forth to make sure that you're not overloading a particular server, that you're balancing the load fairly and so forth. Okay. So these are things that make it very highly configurable. And reality is the client application really doesn't have to pay a lot of attention to what's going on. The client application is essentially unchanged, because that proxy is the proxy that's making the decisions, as well as the server side sidecars are all being provided by the service mesh. Okay. Another key concept in load balancing is where we make this decision of load balancing. Do we do it at L4 or L7? Now, when we say L4 versus L7 load balancing, we're talking about connection-based load balancing versus stream-based load balancing. Okay. Really the difference is where is the load balancing unit, and this corresponds to the OSI model. Now in L4, when you say connection-based, gRPC channels, a channel in gRPC is usually, it doesn't exactly correspond to a single connection. It can be really 0 or more connections, right? They correspond to a gRPC channel, but it sort of relates to that. So the TCP connection is one level, and if you can make your decisions at the TCP connection level, they're very efficient. Right, because you only need to see things from the packet headers. You don't need to do any packet inspection. You just look at the first few bytes of the packet headers and you're done. On the other hand, if you have to make L7 decisions, you could potentially make smarter decisions, but it is more computationally expensive to do so. The thing is that L4 is probably pretty good when you're just dealing with HTTP 1.1 REST-based APIs, where sort of each piece of information from, where each different API call is going to invoke a different connection. Each RPC that you're creating over your REST is invoking a different connection. But that's not true with gRPC. gRPC uses HTTP 2. And one of the reasons, there's a couple of reasons why gRPC with HTTP 2 is more efficient than HTTP 1.1. One of them is, well, HTTP 1.1 and REST. One of them is we have protobufs as a structured data format, a binary data format that Kailash spoke about, compared to, say, doing it with HTTP 1.1 and JSON. Another one, though, is that HTTP 2 is more efficient than HTTP 1.1 because you have parallelism within the connection. You can have multiple streams of data within the same connection. You don't have to have a bunch of different connection startup overheads in order to move data in parallel. So gRPC is HTTP 2. Every RPC is a separate tagged stream within a single TCP/IP connection. Yes? It's a great question. So what happens is on the proxy, in the client, excuse me, when the client wants to start a connection, it'll call, like, the syntax is different in each language, but say we're going to be using C# syntax in most of this presentation. You'll say like new channel with some such and such arguments. It's similar in C++. You'll say gRPC new channel. In fact, it's called it. Yeah, create channel. Excuse me, create gRPC create channel in C++. And so you'll have that with its given arguments. And at that point, when the client wants to initiate a channel, it will then potentially create a backend connection. Now I say potentially because the thing is that if you have two channels from the same client going to the same backend server, it could actually just share those with one connection. It will actually share one connection if it's possible to do so. On the other hand, it could also say, once that connection goes, once a channel, if there isn't a lot of RPCs going on, it can actually back it off and go down to 0 connections. So it can, that's why I was saying 0 or more. It could be 0, it could be shared by multiple channels. It could be, you could have multiple connections for one channel. It just depends on how you want to, what the load is on your channel and so forth. You can make that decision dynamically. It can remain open for a long time. It can remain open for a short time. It doesn't have to close. Sort of morally or logically, there's no connection between the lifetime of a channel and the lifetime connection. No relationship between the lifetime of a channel and the lifetime of a connection. They sort of have some correspondence. Of course, the data has to actually move across the TCP/IP connection. So when the data is moving, there has to be a connection alive. But a connection can live shorter than a channel, or it can live much longer. It just depends on what we make these decisions based on the existing load and so forth, and memory capacity at the given client or server at the time. Great question, though. Any other questions like that? Okay. So as I was saying, the RPCs are separate tagged streams in the same TCP/IP connection. So in order to really make this work correctly or efficiently, you want to have L7 load balancing in your story for gRPC load balancing. A potential issue is that if you use Kubernetes and the default load balancers that are provided, like cluster IP or load balancer, those are L4 load balancers. So you don't get the full benefit of gRPC load balancing. So we'll talk about how to get that, because you want to use Kubernetes, right? So you just don't want to use the built-in models of Kubernetes load balancers. That's all. You can combine them, though. You can have an L4 at the front end feeding an L7 at the back end, which is actually a model that we're seeing more of now. So that way you get a first cut, fast, efficient splitting up of the spraying of the traffic, and then you get your finer grained one after that. Okay, so some of the load balancing options are there. That was the theory side. Let's look at the actual implementations or solutions that you can use. There's the Envoy proxy, which is a high performance. It has dynamic configuration without any restart that's required in order to make it work. It's open source, and I think it was originated by Lyft, but there's a lot of Google developers working on it also. It is highly extensible, and it has really excellent momentum in its GitHub repo and everything. Okay. NGINX is another very popular project. It is quite high performance, and as of the March 2018 version 1.13, they have explicit full gRPC support, so they can do full proxying of gRPC. So those are some nice features there. Basically any proxy that supports both HTTP2 and load balancing should work just fine, though. But those are some that we know to be working, that we know that people use. Okay. If you want to use this in a service mesh model rather than just a simple proxy load balancing model, Envoy or the Envoy working with Istio is one common deployment, as well as Linkerd, which you mentioned earlier. Those are also great. Sorry? Oh, excellent. Conduit. Okay, I'm not familiar with that, but yes, there are certainly others. Client load balancing, as I mentioned, gRPC provides DNS round-robin load balancing if you just want to have something that works right out of the package without having to install yet another solution. But like we said earlier, that's limited because you don't really get full benefits of load balancing. Okay. That was an overview of the current options of the load balancing for gRPC traffic. I want to talk about how to run some of these on Kubernetes clusters. Time is kind of limited, I know, but I'll give you this link to my colleague's examples that he created. Don't try to spell that Czech surname of his. Just look up the word gRPC load balancing Kubernetes examples. You can look it up on Bing. You'll find it, gRPC load balancing Kubernetes examples. You can find it right away, no problem. So, but basically, if you want to do this, if you want to do basic round-robin load balancing of your gRPC service that's run on Kubernetes, you're going to want to create what's called a headless service, one with cluster IP none. Why are we using cluster IP none? To explicitly disable cluster IP, because as I mentioned earlier, cluster IP doesn't give the load balancing model that we need. Okay, so all the replicas will be exposed through a DNS entry here. You're going to set your load balancing policy in your gRPC client. So this is using C# syntax here. So you'll say new channel option of gRPC.lb policy name, comma round robin. So that way gRPC itself will know that. Of course, there's different syntax in different languages. In C++, those would be called the channel argument. So we have similar syntax to do the same thing. And then you connect to the service as usual. Ask for a new channel with the service and service name and port number, excuse me. And then from there on out, it's just going to work. So this was what you were already doing if you were just running basic gRPC, and then this is what you're going to do to make it load balanced. So it really isn't a substantial change in your client applications. However, that said, this is round robin. It doesn't take any server load into account, just the basic DNS round robin that was provided. Okay, questions? This is L7. So that's why we disabled cluster IP none. We wrote cluster IP none first to basically prevent that. And so what's going to happen is that gRPC, when it gets the DNS entry, when it resolves that name the first time, it's going to get the full DNS entry. So it's going to remember all of the IP addresses associated with that service, with that actual backend name. And so in the future, when it's every time you spin up a new RPC, it'll decide, am I going to send it on this channel or this channel or this channel, depending on which IP I'm going to choose. It's going to base that in a round robin sense. So it is actually L7 because it'll make that decision on every RPC, not just when you create the channel. So that's a good question. Actually, I don't know the answer to that. The DNS entries, it will, of course, every DNS entry has its timeout associated with it. So if your DNS server specifies that, it'll do that. Additionally, I'll say one more thing, and I don't know how many people are using this in prod, but you do have an option in gRPC called gRPC connection max age, which you can say that this is a maximum time I'll let a TCP IP connection survive, and beyond that, I will force a restart of another connection. So both of those things, gRPC would consider both of those. We do consider the DNS TTL that's specified in the DNS record, and we do consider, we have our own parameter called max age that tells you how long I'm going to mention max age a couple slides down. Yeah. So, but this allows you to do L7 load balancing. And that's why we just started with cluster IP none to disable the L4 load balancing in Kubernetes. Okay. And if you want something more complicated, like a service mesh, the reality is, again, the example is the code is in the example, but the basic steps of this, you're going to install Istio in addition to having Kubernetes, and you're going to do this Istio control kube inject. What that does is it actually provides your sidecars and proxies. It actually puts those into your pods, separate containers, and makes sure that those are the thing that the actual connections are going to. You're going to use port names for your service. You can use the port name gRPC or gRPC dash, whatever you want to call it, and that will be recognized for the routing. So your routing rules will then be reset based on that, and that's going to be how your Istio service mesh is going to actually take care of your load balancing. So now you don't have to make any changes to your client application. All you're doing is making changes to your configuration of it. Your client application will just call new channel just like it always has, and it will then automatically get load balanced through these sidecars. Your server, I should say, your server applications also are not going to look different. Basically, all of the actual control of the load balancing side is going to be taken through the proxies that are added for you by Istio. Pretty close to wrapping up. I think we're running short of time now. One thing I want to just quickly mention, compared to sort of conventional or traditional RPC models, which are single request, single response, gRPC is a little bit more complicated because, as you know, in gRPC, as Kailash presented earlier too, RPCs can be streaming. We have bidirectional streaming RPCs in addition to unary. So RPC isn't really a single atomic unit of work. An RPC can be a long-lived thing. Load balancing, though, is done on a per call basis because each call can have its state associated with it, right? Not only at the actual gRPC library, but at the server itself, right? The server is probably going to have some state associated with each call if the call invokes a method handler. So that's an issue. So if you have long-lived streaming calls, there's not any balancing happening during the length of a single streaming call. And it's complicated. I say can't work around with waits. You could potentially if you knew what your duration of your RPCs was going to look like, but it's still probably complicated to do so. It's complicated or extremely difficult or impossible to work around this by putting weights on your L7 load balancer by saying this operation is 10 times more expensive as that one, because you can't always be sure. There are options. One, restart your streaming calls periodically. Just make sure that in your code of your streaming call, after 3 requests or 10 requests or whatever, you're going to say, okay, that's it for now, but it's an API design thing. You have to design your API to be able to tolerate that, to be able to deal with that. Another is to set this max connection age. set your max connection age to limit the lifetime of a given connection. But again, with it, that only makes the decision when you're starting a new connection. It doesn't kill an existing stream, for example. So that also has it's not. It may either needs API change or you need to think about that. But this is a basic challenge that when considering API design, you have to think about using streaming sort of carefully, knowing that streaming does interfere with load balancing. Once you've started a stream, they're great for efficiency because they don't have continuous sort of RPC setup overheads. It's just actual data flow at that point, data pushing back and forth, but it does interfere with load balancing. So if you want to have a well load balanced solution, you should probably either have your API such that it's either pure unary, or if you have streaming, limit the lifetime of a given stream so that your load balancer will kick in. Okay. So that's just one thing that we want to draw people's attention to. Okay. We have more to talk about, but of course, we are short of time. But the basic thing I want to bring up, though, is that we are an open source project. We do love your contributions and comments. We welcome them extremely. We have some of our key links there. Just if you can't find anything else, just remember gRPC.io, 6 letters. gRPC.io will take you to all of these things. You really put mail to in there, Kailash? Okay. Yeah, okay. Yeah, just gRPC.io. That's all. That's all you got to remember, gRPC.io. Okay. And so I'd like to turn it over to questions. Thank you so much for asking them during, but if you have any more, now's a great time. Chris. That's a great question. So the question was about stateful load balancing or stateful routing. Can we use state to just make some decisions, and does Envoy allow us to do that? So this is like sort of moving from load balancing to sort of say sharding, right? To sort of, I actually don't know the answer to that kind of decision based, yeah, but.
No, I'm just gonna hazard a guess that it's possible to sort of use metadata sort of things.
Right. You can certainly use metadata and code that information. I just don't know if any of these do it out of the box. Is the thing that I'm not sure which of any of these load balancing solutions would do that for you just automatically, or if you have to do additional configuration to make that happen. Right. Right, but can you do method affinity, for example? That I don't know the answer to off the top of my head, or do any of these automatically provide it for that? I'm not sure. Right. Yes. So the question was, with the channel abstraction in gRPC, how does that interfere with the load balancer? So once a channel is created, can it connect to different backends? Absolutely. The channel is basically, once the channel is created, you will get the DNS record for that backend name that you've given it, but it won't just connect to the first host that's given, right? It'll first backend IP address. It might connect to this backend IP address this time, but on the next RPC call, it might connect to a different backend. So one channel can be 0 or more connections. That's what I really want to get back to. That one gRPC channel can lead to multiple connections. And so that's really what enables us to do round robin. Okay, I just want to quickly throw up our feedback survey. If you get a chance, it's bit.ly/2 capital LAUXAB. This one's a little harder to maintain. You might want to take a photo of this, or I think it's recorded. Right? Yeah, it's recorded. So awesome. So yeah, so we'd really appreciate it. We have a survey, and if you could give it to us, if you give us your feedback, we'd really appreciate it. Thank you very much. Thanks, Tristan.